In this chemical reaction, we have an alkene, and we also have an aromatic functional group. Aromatic functional groups do not react with simple things like hydrogen bromide, so we don't want to touch that. Now what we want to do is again use Markovnikov's rule to place the hydrogen on the less substituted carbon and the bromine on the more substituted carbon. So let's show the mechanism by taking the pi bonding electrons of this external alkene, attacking the hydrogen of my acid, and draw the carbocation intermediate. This carbocation intermediate can be drawn by adding once again the hydrogen to the less substituted carbon and the positive charge on the more substituted carbon. You might classify this carbocation as secondary, but it has a special name when it's next to a benzene ring or a phenyl ring. We call it a benzylic carbocation. The reason why it has a special name is because we can draw numerous resonance structures of the carbocation that show how it is resonance delocalized and therefore quite stable relative to just an ordinary secondary carbocation. So I won't draw them all here, but just make a note that many more can be drawn. Now, our carbocation is great here as a benzylic carbocation, but it's still going to react with bromide to provide the final product. So we use the negatively charged nucleophile bromide to attack the positive charge of the electrophile, and that's going to give us, at the end of the chemical reaction, a benzylic bromide. Now, this bromide is formed by the bromine attacking the more substituted carbon, and the hydrogen that I've added does not need to be drawn in this organic molecule.